comes back, it's at a certain place, and that can be measured. And if you circled around the world and came back 12 days later, sent out another wave in that same controlled way, it should come back in the same phase if nothing's changed on the Earth's surface. If it has, if there's been an earthquake or some sort of movement on the Earth's surface, that phase will not be the same the second time around. And so what makes phase useful for most applications is comparing two sets of phase data, so from two different acquisitions. And that's where interferograms come in, where you compare the phase of two different dates that are acquired from about the same place in space, and you can see where the differences are. So this is an interferogram of the earthquake last month, just here in Northern California. And you can see very clearly that where the fringes are tighter together, that's where there's more deformation. And then the wider fringes, there's less change that's happened. So the radiometric terrain correction and the interferograms are kind of the first really useful step that brings data to a wide variety of users. So how do we get that data to users? So as I mentioned, we're a distributed active archive center of NASA, and we have a pretty well-defined mandate of what our job is to do. And we have not been approved to process higher level products and distribute them on a wide scale at this point. And so we're stuck in this place where we want people to be able to use SAR data. That's our mission, is to make it accessible. And yet how do we do that if we don't have these products that are actually ready to use without being a SAR expert or without having to do additional processing to get to that point where you can look at it and get some information out of it. So we have a variety of tools and resources. I'm going to go through them quickly, but first I want to mention, if any of you are familiar with our Vertex data portal, it has been totally overhauled. So we have a new data search web portal. So check it out, it's much faster, it's got a lot more filtering capabilities, and it's a really cool platform. And so we'd love to hear if you have feedback on it as well, but check it out and download some data. So starting from the least technologically advanced of our solutions for getting analysis-ready data, we offer a number of different data recipes, which are basically step-by-step tutorials that take you through the entire process of either creating a radiometric terrain corrected product or an interferogram, or we have a number of other different processes that we walk a user through. And you don't have to necessarily know anything about SAR when you're first starting with our data recipes. It kind of starts from the first step and walks you through that process. So check out our site for the data tutorials page and see if there's something that might walk you through a process that you're interested in. Similarly, we offer a baseline tool, which is, it's through the data search portal. So any granule that you select, you can click on the baseline tool option, and it'll suggest potentially good images for using for interferometry. So if you're wondering what's good to compare, this kind of narrows down your options for you. And they're all within the critical baseline, so they're close enough together from their acquisition point in space so that you could be comparing them in a valid way. So this gives you sort of the options available in a visual way. If you want to know more about this, come and talk to me afterwards. I could talk about this for 20 minutes just by itself. So, but that's a tool that we offer to help people decide what granules are useful for running interferometric pairs. One new product that we've been working on is creating advanced product toolboxes for desktop processing. So there are open source software out there that you can go ahead and use to do your processing, but a lot of them require a fair bit of installation. So especially for the INSAR, installing ICE on your own computer, there are a lot of dependencies. It takes a long time. It's a little bit challenging just to even get the software ready to go on your machine. And so if you're looking to make an interferogram, there's already this software acquisition hurdle. Even though it's free, doesn't mean it's easy. So our Getting Ready for NISAR team has been developing these Docker containers that have all of the software that's required, including all the dependencies, so you don't need to install anything else. As long as you can have Docker installed on your computer, you can download this Docker image and run it with a single command, and you just give it 2 granule names, it starts running, and you've got, I guess for the RTC, you only need 1 granule name, actually. You just put in the granule name, and you're ready to go, and it's processing for you. Unfortunately, Windows and Docker don't play very well together, so it's a little bit more difficult. We haven't come up with a good solution for that. But if you're a Mac or Linux user, you can just install Docker, download this package, and use that image to process data. The RTC tool is already ready and available, so you can go and download that. And they're also working on one for interferometry using the ICE software package. We do have some products that we have already processed. So we did get permission to process all of our ALOS Pulsar 1 imagery that we have in our archive to radiometric terrain corrected products. And so those are all ready to go. They're available in 12.5 meter or 30 meter pixel spacing, and it's projected to UTM. You can just go to our web, I keep wanting to call it Vertex, that's what we've been calling it forever, but our data search portal. You can just go and search for the ALOS Pulsar mission, and then under the More filters, there's an option to select the file type. Just put in the terrain corrected, either high res or low res, whatever you're interested in, and it will return an already RTC product. So this is an L-band data set from 2006 to 2011. And with the new NISAR mission that's coming out in 2022, that's also an L-band mission, so there could be some really interesting potential for decadal comparisons. So that's a pretty cool data set. So in order to process that RTC data, we wanted to leverage cloud processing because it's pretty computationally heavy. And so we developed a hybrid pluggable processing pipeline, or HYPE, and it allowed us to utilize cloud processing in order to run all of our RTCs. So once the Pulsar mission was done, we wanted to continue developing this platform so that we could have Sentinel-1 products as well. Even though we can't offer them as a standard product at this point, we want to be ready in case we ever can. And so we've developed the HYPE system to be able to deal with all kinds of SAR processing tasks using Sentinel-1. And it is open for testing. It's a beta platform, but if you're interested in checking it out, we would love to get feedback. The more specific, the better. So you do need an Earth data login, as is required for all NASA data downloads. And then you need to visit our ASF search portal, where you can accept an end-user license agreement. And then once you log in for the first time, you are prompted to send an email to activate your account. And then you can go in and access all of the various processing options. So HYPE is really designed to work around a subscription approach. So you just enter in an area of interest and a date range, and then select the process you want and the options that are available for that particular process. You press go, and HYPE goes out and finds all the applicable data granules and starts processing them immediately. And we'll send you emails as they are available, or you can just wait and go to your subscription page and download them as a bulk, or whenever you're ready for that data. There is also the opportunity to just do a one-time processing. If you have 2 granules that you want to process for RTC, you can just go to the data search portal and copy those IDs and paste them in there, and then you know exactly what you're getting and how many you're getting. So if you sign up for HYPE, you have a pretty small quota. It's only 25 granules a month. And if you enter a subscription, it's a good idea to go to Vertex and check to see what's actually going to what will be returned based on those parameters, because you may be surprised how much data comes back from your area of interest. And so it's pretty easy to max out your 25 granule limit in the first 5 minutes. And so be aware what you're entering in before you go. So the products that we have available currently on HYPE include RTC products, both for Gamma, which is a proprietary software, but also Sentinel-1 Toolbox, which is open source. Our Gamma product is kind of the most well-developed, but we also have the S1TBX is ready to go, so you can check that out as well. These ones we've packaged up with metadata, so there's an XML file for every raster that's included in the package, and they're actually readable within the ArcGIS environment. So if you're looking at stuff through ArcMap or ArcGIS Pro, you can just go to the item description and read all about it. So We also include a README text file and browse images and KMZ files and all kinds of stuff, all packaged into a zip folder. We also offer the option to create an animation out of your subscription. So you can go to your subscription and either choose everything or just a few key frames that you want to animate and generate a GIF, as well as all the individual TIFFs that go into creating that GIF. And that can be really useful as a visualization tool. So if you're looking for change at a particular area, running a quick visualization just to pick out where you may want to focus your efforts, that's one approach. We also support 4 different processors for INSAR. So again, our most kind of well-developed product is the Gamma, using the Gamma processor. But we do have options for GMT5 SAR, ICE, and Sentinel-1 Toolbox. We don't have as much metadata yet developed. We're still working on writing up the README files and things for that. But you can download them, check them out, see if they meet your needs. And if you have any suggestions, please let us know. Again, you can run time series using the Giant software package, which is designed to look at the short baseline and near short baseline INSAR time series analysis. We have a few other random products. There's a color decomposition product for anything that's a dual pole or more. We can create a false color image using the VV and VH channels. So it's not necessarily true to Earth. Sometimes deserts show up looking like oceans, but it can sometimes help you digest visually a little bit better the SAR data. We also offer an RGB difference image, so it's looking at changes in the VH, and any areas of change are indicated in the blue channel. So if you see blue, something's going on. We also have a pretty simple threshold change detection product, which just takes the log difference of 2 acquisitions and then applies sort of a random threshold. So this particular threshold that's automatically applied is pretty large, so it's going to only pull out really extensive change or areas of large change, but the actual difference raster is packaged up with this, so you can go to that difference raster and threshold it to whatever you want. So if the change that you're looking for is pretty subtle, you can choose and reclassify your raster based on that. And lastly, there is an API for HYPE, and also if for those of you who are not as familiar with our Vertex, or formerly Vertex, now Data Search Portal, we also have an API for that as well. So if you want to interact programmatically with any of our products, either the ones that are standard in our collection or any of the HYPE products, you can do that programmatically. So.
Great talk.
Do you want to do questions? Okay.
We have about 5 minutes for questions, and if you could step up to one of the microphones, that'd be great.
Everything's all clear.
Hi. You mentioned somewhere in the slides about flood detection. Do you
Yes.
have an output product or?
We don't have a standardized product, although the threshold change, that's actually a flooded area. So like there's the red part there that really, the flooding does get picked out. And there are, in many cases, you can use a simple threshold because especially if it's still, if it's a calmer, the waters are calm, you can just apply a pretty basic threshold and pick out water pretty well in a very unfancy way, but something that you can do just in a GIS pretty quick and easy. So if you want a quick solution to identify flood zones, that's a simple way to do it. So that you could either use the change detection product or just look at a single granule and often get pretty good results. So. Mm-hmm. Anything else? All right. And if you have any other questions, feel free to come talk to me.
So you're going to put it up by your collar, like your collarbone, and then the audio comes out. Yeah, I was trying to put it on.
Just borrow that for a quick second. So I did just have kind of a side question about the open sourceness of our code. And all of the HYPE code, the wrapper code, is open. So you can go to the ASF admin section of GitHub and find the hype code. So Gamma is a proprietary software, and so you wouldn't be able to re-implement that. But all of the other ones, all of the other software packages, you could install and run hype yourself.
Yes. ARD 2019. No. Previous one.
This one.
No.
Oh, this guy.
No.
Sorry, I'm not.
Sorry.
okay.
Afternoon. ARD
This guy.
20. Mm-hmm.
Great. Next we have Alex Kudriashova from Astro Digital, and she's going to be talking about data calibration of Landmapper-BC satellite version 1.0.
Hello. My name is Alex, and I'm a data engineer at Astro Digital. So at Astro Digital, we do small satellite missions as a service for our needs and for other companies based on CubeSats with a standard 6U or 18U bus. So the mission I will talk about is Landmapper-BC for Earth observation. So the initial goal of the mission is to be a part of the daily monitoring of the world agricultural lands, like in addition to complement Landsat and Sentinel for the missing dates based on CubeSats. So a couple words about how the mission is looked. So we, based on small sats, we had 2 successful launches of Landmapper-BC 3 and 4. So Landmapper-BC 3 was launched about 3 years ago, and it's our satellite for testing and operation and telemetry experiments. And the BC4 is the satellite we currently regularly image the data and collect the data with. So it has the wide swaths of 220 kilometers, and we have the sun-synchronous orbit within an hour from Sentinel-2. And the GSD for data is 22 meters, which is like between Landsat and Sentinel. And we tested our downlink, so the current best result is 320 megabits per second, which is like 2 times higher than in this slide. I'm terribly sorry for not fixing it. And given this, we know that with K-band and with this speed, we can downlink the data from Svalbard within 90 minutes after the acquisition, so the fully collected swaths. And given this, we are confident that we can deliver the data within 6 hours after the acquisition. So the main applications for the data is the agricultural monitoring, disaster response, and primarily the monitoring of the green mass because of the spectral bands we have. So we do red, green, and near-infrared bands with separate sensors, and also we calculate blue band and validate it against Sentinel. But this is more for visualization purposes. So it's like just computing. While the red, green, and NIR we use it for green mass assessment. So the values are similar, like close to Sentinel-2. So that's why it's our obvious target for validation. And regarding the capacity, so here is the image of our capacity, for example, of the Corn Belt AOI. So we image like within this large, like 1,000 kilometers area from 7 to 16 times every month. And this is how much data do we produce. So, and regarding the data quality, we don't have that much imagery yet because we were still like finishing our commissioning phase and playing with different parameters. But the MTF estimation is good just for having one picture. And meanwhile, it was a little bit challenging to find a proper target because of 22 meters, and we wanted something consistent dark, around something lighter, and with an area like at least 10 pixels in a row. So we found this target. It was the solar farm in Morocco, and we used it for assessing the MTF because it's like a bright dark area around the desert. So we reached these MTFs with given exposures, and we are quite happy with these results because we almost reached the lab experiments, And given this, we are like less than 2 pixels around, confident of where we are. Regarding the radiometric calibration, this is still more work in progress, primarily because we were very unlucky to target Railroad Valley, California this year, because I have the collection of all the clouds over the Railroad Valley, California. So we still don't have the data to start doing. So the best thing we can do is try to find like this very similar thing to what colleagues from Planet were talking earlier today, is how do we do the cross, like the acquisition the same day with Sentinel-2. And we are lucky that we are like within an hour after that to see that what areas do we correlate and how much our corresponding spectral bands similar to theirs. And so we found one of these images. So this was May 10 over Central Valley, California. And yeah, so the visual product with like some of the min-max stretching looked great for both. But talking specifically about the values response, I a little bit narrowed the area and did some pre-processing. First of all, I downsampled Sentinel to GSD. It's really great to have Sentinel 4 times higher than us. So that's why we can really downsample it. Took the flat area for easier and more confident band co-registration, and took the target to be fully agricultural because we don't have blue band, and for example, for water bodies, we probably won't have that correct, smooth correlations. And the area was 3,000 over 3,000 pixels. So we took the, so we co-aligned 2 images and plotted the pixel values from both of them on X, Y. And here are the results. So again, so this chart is zoomed in to the wider area of where the growing spectral band has response. So basically within this 3,000 by 3,000 pixel sample, there were no water bodies and not so much values out of this range. And here is the NIR band, and the red and the green. And while we are waiting for the Railroad Valley or Livia 4 images, so this will be our continuous experiment to see how statistically we correlate with Sentinel-2A in other locations. So meanwhile, we rolled out our first data sample for the orthocorrected, not radiometrically corrected data. And so here are just the nice pictures for many locations. So we have Central Valley, California, Corn Belt, South America, Middle East Asia, Australia, and China. And primarily for all these areas, we are ready to share the data to show that it accommodates the current time series and can be used all together with Lancet and Sentinel. So it's located in our both. We have copies in Google GCP and our AWS storages. So feel free to email me. I can just send you a link to the data to start playing with. Thanks.
Thanks a lot, Alex. Are there any questions from the audience? We have about 5 minutes. We can do a round.
I have a quick question about something we haven't discussed that much in the conference, but it's kind of, I would say, lurking underneath some of the analysis we do, which is, can you say something about how the band alignment is done? What approach you've taken to band align, and what's the band-to-band co-registration performance you're seeing? Because these are like 3 different board-sided payloads, right?
Yes.
The way it works. So I'm curious about how was the performance of band aligned in those 3 payloads?
You mean geometrically?
Yep.
I will have a fixed offset.
Okay. So are you ortho in the 3 different bands individually on top of a base map and a DEM, or are you geometrically solving the multi-view problem and then doing an ortho?
Okay, so there are 3 bands.
Yep.
We ortho the central, the sensor 2, the red one,
Mm-hmm.
and the other 2, they have a fixed offset against it.
Okay.
So,
Cool.
so like geometric is like the same like parts of the sphere. So we just do that offset.
Okay.
It's like it's a static value.
Yeah, thank you.
Thanks.
Thank you.
Thank you.
We can just plug in the VGA. I think it's pretty straightforward.
Yeah, so that's it.
You want to put
Great.
it up here?
Next up, while we get set up, is Tony Butzer from the USGS or Contractor?
I better say I'm a contractor.
Okay.
And I'm not sure I should say I'm affiliated with any organization, quite
Okay.
frankly, about this talk that's about to be given.
Okay, representing himself?
Exactly. I like that. Thank you. That gives me a little leeway. Hey, thanks for letting me share today. I'm Tony. I'm a cloudaholic, and you can help me. You can help me with a few things. I got a lot of confessions. In fact, probably 45 minutes worth of confessions followed by a presentation. But I also suffer from split personality disorder. So I got a couple of personalities. One of them I call Anthony, and Anthony's good at giving really clinical presentations on just facts and data. I got another personality I call Tony, and he gives a little more candid, blunt presentation. And I figured since it's 2 o'clock in the afternoon after everybody's had lunch and a lot of long, detailed, complicated presentations, we might let Tony go. So if you guys are okay with kind of a candid talk, raise your hand. Excellent. And again, I do not represent any organization that you might have heard of, just to protect several people from this talk. So I just wanted to share this. There's a lot of people that give succinct, straightforward advice, and this is some of the best I saw. And this is by the Pangeo folks. And I'll talk a lot about Pangeo in this talk, but or if allowed to anyway. Portals and how do you do the next big data portal? And this was incredible. So step 1, place your big data in a cloud object store with self-describing. That sounds a lot like COGS and STAC. Congratulations, you're done. And then he ends with this. Sorry. Maybe. Go slower. It's over. He says it's over. Go home. It's Ferris Bueller. So, and I agree. One of the presentators said here's a fact, and I agree. I agree. That's the way to do that. Let's see. All right. So the other thing this talk's going to have is time travel and time and space travel. And we're going to start with some space travel, but which is really cool, and that's why this is going to be a fun talk. But and then I got a new application just from one of the earlier speakers had this problem with Windows, and I got to thinking I can apply this time and space travel, and I can go back to the dark ages and grab our IT departments and have them eradicate Windows, and then we would all be in better shape. So because we could run Docker and other things. So that's an idea I have. So the other concept is that's backwards in this world is that we go to a portal, we write a machine-to-machine interface, and we pull down this data, and we search for it, and we grab it all down and put it on a local disk. And everybody's explained this problem, so I probably shouldn't say much more than that. But the other model, what I think the feature model is, we teleport to the data. We put the data out there in a nice, easy way to use it, easy way to index it, easy way to find it. And as ARD, although that was another great idea the guy had, Sean, this is worth the price of admission. Sean said, imagine, this it works for this demo too, so I'm going to use that same technique. Imagine that the data that you're going to see is ARD. And yeah, that's got to make the USGS feel great, because that's another, we can run on that for another 2 years before we put ARD data out. Just imagine the data you have is ARD. So for this demo, that applies as well. So here we go. Thanks to Open Data Cube, this is their infrastructure, this is their sandbox, and we'll talk a little bit about sandboxes. But you know, this is like your captain speaking. We're about to head to Portland, Oregon, where our data is, and your flight will be approximately 15 seconds. When we get there, the atmosphere will be exactly like it is in this room, because we haven't left. And there'll be a bunch of ARD data that we can exploit. And so that's pretty cool. So you've got, you've got a server. So in here, Christy Klein talks about processing the data in the cloud and says that's not really the point. The point is the point of the cloud that's really exciting is the access characteristics of the cloud and the scalability of that, and being able to get it from single stream networks instead getting it from those networks, you get it from a distributed file store. So there's just that much more agility and speed. So this is pretty cool. You get a container, which is essentially, think of this as a computer, think of it as an instance, whatever your favorite virtual paradigm is, that's what this is. You get that by just click a button. I mean, they had to dumb I joined the Open Data Cube, they had to dumb it down to a start button for me. And I could finally start up something and work on the Open Data Cube, and they've done a fabulous job of engineering their stuff to run in multiple environments. Along with that, if you really want to get your geek on and you can't stand notebooks, and I'll get to the scientists in a minute. You know, this is where I want to live. This is where the engineers who do all the real heavy lifting in the world. And we'll talk a little bit about those scientists want to live. But the scientists want to live back over here in notebook land, so we'll go back over there and I'll talk slow for some of the scientists. But anyway, so here's a demo, and the concept of this is it was a lot of simple ideas brought together in a demo in a fairly quick amount of time, and I've got Matt Hansen and others to blame for this. I got some scolding from Matt in a minute about making things too simple. I mean, I don't know if he's ever programmed any job security into his life, but when you make it this simple, anybody can run it, anybody can code against it. You've really got to add some obfuscation and complications to this stuff, or you know, it just won't be sustainable. So here's my notebook, and this is extremely robust. This runs everywhere. Not the notebook, the infrastructure. So I'm just going to go ahead and let this run. And this notebook is extremely under-sophisticated, but with some imagination. You start with imagining this was ARD data, and I still like that. Imagine this is all perfect ARD data. And then there were some aspects of the full-blown Open Data Cube that I wanted to kind of prototype a different method that might fit the STAC cog model natively better than the Open Data Cube. And by the way, the Open Data Cube is a Pangeo reference architecture implementation, which is totally by accident, but extremely fortunate and really cool, really cool. So everything I do from now on will be a Pangeo reference architecture implementation. So we have this example notebook, and maybe it's running. We'll see here now. Here, so I'll start here maybe. So this is the problem I have with Matt. He names things like red, green, blue. I mean, you'd think studying image processing, you know you want to name it band 4 and then move it around so people can't find it, or some frequencies that only the physics geek, you know. Like I said, you got people like me running this stuff now, because red, green, blue are terms that I can understand. So thanks for that, Matt. So anyway, that was the load piece, but I want to walk back quickly. I'm going to run out of time, obviously. What I'm excited about is, and these are methods that were stolen from the Open Data Cube and they have a data cube, something equivalent to a data cube search, and something equivalent to a data cube load. And then they have measurements, and they have an AOI. And the AOI is a GeoJSON file, and those are easy to create, and they're easy to understand. And then you have your measurements, and you tell it to search. And what this does is search the STAC catalog that's out there for the public data set and brings back your asset list. So everybody with me so far? So, and yeah, I print debugs all the time because I introduce a lot of bugs in code. That's why I'm not too worried about people getting this from GitHub. But it is out there. And then abstractions. So what are some of the really powerful, cool abstractions in Python? And there are many. Rather than return a data object, some sort of customized Python data object, why don't you return an abstraction that everybody can do cool stuff with, that already has a set of tools and ecosystems and documentation. God, I don't want to do documentation. So documentation around it. So I return a pandas data frame. And then you can also prune against that. And you can prune against that in a lot of ways. So all of this is kind of a prototype for how you might create something that John Dwyer, and I'll get to John Dwyer too. That's coming. But how you might prune and get to what John Dwyer wants. So here's my area of interest over Africa. We've been doing some work in Africa. There's the load. So the load also has an AOI and the measurements and the data frame of the assets. So it knows where to get those, where to go out and do these HTTP range gets to grab the pixels and throw them into an X-array. And X-arrays are completely awesome. So, and I believe he was a climate guy, an ex-climate guy that did those. So here's my observations, 61 observations, fairly small area of interest, 151 by 230, all instantiated in memory. And then you can do really cool band math, you can do ND-value, you can do all kinds of neat stuff with an X-ray, you know. And the Open Data Cube has been doing all kinds of neat stuff with X-arrays for years now. So they have a set of applications and science workbooks that operate on an X-ray. So if you give an Open Data Cube guru an X-array, they can do cool stuff with it. And remember, this is ARD, so I could do time series with this if I wanted, because it's real live ARD. But I'm not that smart, so I do weird stuff like this. And I wasn't going to get political, but this happened during the government shutdown. So when I was looking at this, and by the way, when I lose my job for giving this talk, I'm going to become an image analyst guy. So because I picked the best color maps. So natively out of X-array, you can throw a plot up without doing anything. So this is a lazy person's dream. This whole ecosystem that these guys are building is a lazy person's dream. So I throw the red band at this weird prism color map, and I got to look at this while I was heavily drinking and during the government shutdown. And I picked this because it kind of has a fishtail. But if you're not careful, you start seeing Donald Trump's head in there. So forever some of you people are going to say, and I didn't draw this, guys. This is something we would give Charlie Trotwine and say, where the hell on earth is? Oh, that's Donald Trump's head in the lake. So, and that's enough I'll say about that because it'll get me in trouble. But if you steal code from the Open Data Cube folks, and then you rebrand it as yours, you can actually do RGBs, and man, there's a science in colorization, and that's not me. And you can also say, I want to get rid of things. I can pick indexes. So if I was to do this again and I didn't want those ugly clouds there, I'd get rid of that. But and again, this is all very few lines of code. And then you can animate and then this is for the blind guy, find the movie. So you can animate these things without any effort. That all comes stock out of the X-ray. So, okay, thanks. Gosh, I don't have any time. That's too bad. well, that's all right. So you can do other things. Then I really just want to hit on a few key points. And I'm very passionate about this. I could go on for a long time. This is the Pangeo, and I would argue the Open Data Cube is a great instance of this Pangeo architecture. It's somewhat topology independent of what your physical architecture is. So it runs on HPCs. It's also a community and a concept where they're doing sharing engineering science. And the ESIP lady, Erin Robinson, came up and talked to me and really wants us to get connected, connect these two worlds, Open Data Cube, Pangeo, ESIP, and so on. And also the USGS, as Pete mentioned, has a pangeo.chs.usgs.gov that works identical to this. You authenticate using GitHub, and you're part of that space. Now, right now, it's limited to the USGS network, but Rich Signal, if he gets his way, it'll go beyond that. Okay, so some conclusions, and then I'll sign off because you guys need me to. Free data plus free compute plus brain power equals resource management solutions. It's enabled by a confluence of technologies powered in the cloud, and I'm all in on cloud. Many collaborative sandboxes are popping up that are really offering free compute. Bring your problem, put it in this architecture that's available. Data curation and computer provisioning, two of the big challenges in the past, are now at our fingertips with substantially less end user effort, I might add. The people that are building these, there's still considerable effort, but from the end user standpoint, you can see it's pretty easy to get quickly there. And then the browser will be the JavaScript in the browser. There'll be a lot of applications that are right now native in EXEs that'll be converted to the browser. And finally, the future of Earth observation and data transformed into information application. That application space looks very bright to me indeed. And then finally, I'm very humble to be in this crowd. Thanks.
We have some time for questions, if anybody has any for Tony. Thanks, that was great.
Hi, Tony. Or Anthony, I have a question for Anthony.
Yeah, all right.
Okay, so from a 1,000-foot view, so to speak, the UK Met put in Python, created an abstraction for NetCDF, and that's their Iris Cube. And it's really spiffy, great engineering. And so how would you relate, from an outsider's point of view, how would you relate the UK Met Iris Cube to the Pangeo data cube, like right now?
Very similar heritage. The idea for the X-ray came from the NetCDF. It was really to look at trying to get something that had labeled information for the human, basically a NumPy array with labeled information for the human so that they could easily digest it, but its heritage comes from the exact same place, the NetCDF, with the attributes, labels, measurements. Yeah. Well, my guess is that you should be able to work out interoperability in a fairly straightforward way, especially if you both deliver a similar abstraction. If you intersect, if your meeting ground is either the X array or what was it? I'm sorry, what was it?
It's the Iris data cube from the UK Met.
Yeah, so depending on what kind of ecosystems above that for science, there should be a lot of synergies. Yeah, thanks. Iris. It's great to have real expertise in this.
Let's talk more about that.
Yeah. All right. Thank you.
All right, we have time for another question before our next speaker. So if anybody has anything else burning, feel free to ask Tony. Otherwise, send him a random message. All right, great. Yeah.
It's on there. I transferred it.
Okay.
So it's on my documents.
Oh, okay.
So just go to my documents.
Where's this?
Because I
Boo.
there are two that he asked me, and I don't know which one he wants to.
No, one's a PDF, right? So don't use that one.
So you want to put it close to your collarbone, so up higher is for the recording. I think it's
Something like that?
I think
Cool.
that is should be ideal.
Good enough?
Higher. That's right.
No.
That's good.
Ah, yeah, thanks.
Next up, we have Adam Lewis. And he's going to be talking about stuff. Yeah.
I'm going to talk about analysis-ready data, just for a change. Thanks, Tony, for imagining analysis-ready data. I think that's a good start. Sometime before the Open Data Cube, which was created over a beer in 2016, but after the Australian Geoscience Data Cube, some dudes and Jen from the United States Geological Survey came to GA in Canberra without beer and dropped the term analysis-ready data, at which point I rapidly said, that's a great label, I'm going to steal that. And within a few months, we were propagating that idea within something called the Committee for Earth Observing Satellites. Over a pretty short period of time, it became apparent that people either loved or hated this term, hated it because it meant nothing, or loved it because they liked the idea. And fairly shortly after that, it became apparent that at some point, you have to define and specify what you're talking about, because otherwise analysis-ready data becomes all things to all people, at which point it's going to lose its value. So within CEOS, the Committee for Earth Observing Satellites, which is what that thing is, there's been a fair bit of work happened since late 2016, well in fact since 2015, to put boundaries around the idea of analysis-ready data and to specify what's meant so that we can, in confidence, move forward and produce analysis-ready data as a community. That's reaching a really interesting point in its evolution, and one where it's really natural for this community to start engaging with the CEOS community. So what is the CEOS community? CEOS is the International Committee on Earth Observing Satellites. Many of you will know about it or of it, or have had the pleasure of interacting with it or be part of it. It's the government or civil space-based organisations, 62 members and associate members, 170 missions. You can read those stats. On the right-hand side, you can see the organisational structure. There's a chair that changes each year. Last year it was the European Commission. This year it's the Vietnam. Next year it will be India. And beneath the chair there's something called the Strategic Implementation Team, or SIT, which is sort of the group that run the agenda. That's this year being run by NOAA, and next year it will be taken over by Australia. So that SIT chair is sort of the driving seat for CEOS. And that's relevant because that's the mechanism. We'll be taking over that mechanism sort of next year. Buried deep within the bureaucracy, there's something called the Land Surface Imaging Virtual Constellation, which I co-lead with Steve Laban over there, so if anything's going wrong, look to him. And that group it's lost its way somewhat by 2014. It was re-established in 2015 and redefined its mandate and formed up, now has 20 members representing 12 space agencies. They're listed there, but you can see they're a pretty good global representation. And they started working pretty actively on this idea of analysis-ready data. That has got a lot of buy-in from CEOS as a whole, because CEOS sees itself in a context, a rapidly changing context. It's moving from an era of, well, it's moved pretty quickly in the last few years from an era of really being science missions to being operational missions, epitomised by Landsat and Copernicus. And now it can see what's happening with the landscape of small satellites, and it's looking at how does it fit within this future industry where there is 6 times as much demand for small satellites as there was a couple of years ago. Presumably the figures are much larger than that. There are thousands of small sats and a huge amount of growth in uptake. So clearly CEOS is thinking about how it fits in this environment and what's its value proposition going forward. And indeed, the government's funding things like Copernicus are very explicit that the value proposition is that you create jobs, stimulate the economy. So what are the barriers to that? Well, one of the barriers is the accessibility and usability of data, which is why analysis-ready data makes a lot of sense to this community. So the community in 2016, after a lot of blood, sweat and tears, agreed on this definition at the top for analysis-ready data. It was only allowed to be analysis-ready data for land because it didn't want to get too broad in scope. But really, the words speak for themselves. Satellite data that's been processed to a level where, and organised into a form that allows immediate analysis with a minimum of additional user effort. And interoperability both through time and with other data sets. So by this point in time, we're all doing time series analysis. We can see multiple sensors that are going to have to be used together. What's the basics you need to do that? Really importantly, and one thing that has been struggled with, is that this is not targeted at expert users. So there will still be 10 expert users who will want to use the raw data and process it their own way, but there's another 100 latent users who need and would use the data if it was in a more readily usable form. All this data is accessible, everything I'm talking about is accessible from that website, ceos.org/ARD. On that, there's these 3 documents in the bottom left here which talk about why this is useful, what are the benefits, and it does it from the frame of data producers. So if you're a data producer, having your data analysis ready are going to increase the uptake and the impact, maintain relevance, increase efficiency of use. If you're a data warehouse or a distributor, then your platform's going to have more appeal if people find it easier to use the data. And your higher quality data sets are going to be more attractive. And if you're a data user, it's going to save you 80 or 90% of the time and effort. You're going to be able to get on with analysing the data for the purposes you had in mind when you got into the business. So that's all on the website. And those benefits are generally accepted. So a little bit of a digression. So there's also been a lot of work done, particularly by Steve and Ferron Gascon from ESA, about some other definitions. Once we got to a point of saying, okay, this is going to be a start point for interoperability, the next question was, well, hang on, we can't use these 2 things together. So it's not fully interoperable, but it is a start point. So there's some work being done, and it's just about landed in terms of terms like analysis-ready data, being this data that's been processed to a minimum level for use. How does that help interoperability? Well, it doesn't deliver full interoperability, but there's this concept evolved of a spectrum of interoperability as things get more and more interoperable as you move from the left of that bar to the right. Analysis-ready data is a start point for that, and further down it is where data products are harmonized. And at the end, if you actually fuse 2 products together into a series of numbers and you don't know which source they came from, then you're talking about ultimate interoperability in a fused data set. So those terms are being wrangled with as well, is the point I wanted to make. So going back to the analysis-ready data, what the single real piece of intellectual property that's been put into this from CEOS is that at the top there's a definition which can mean anything to anybody, but then the next layer down is these things called product family specifications. I really want a pointer, but anyway. So those things are the difference there is to say if your data are going to be analysis ready, you really should be talking about it being a measurement of something. So what are we actually measuring? So most obviously optical surface reflectance. It seems obvious now, but a few years ago it wasn't obvious at all. So any instruments that are measuring optical surface reflectance naturally form a family. And if your measurements of that property are reasonably accurate, then there's a foundation for comparing and interoperating those things. We started with optical surface reflectance and then rapidly spun off into surface temperature. Went round in circles a few times about surface brightness temperature and surface temperature and landed on surface temperature. And then very rapidly out of that, the radar community stepped in, and now you just heard about radar and how complex it is, all the different things you can do with it, but there are also some simple things you can do with it. And the radar community stepped in and went almost overnight from a position of you can't do this with radar to, oh, here's a specification for radar. Radar will have many products because there's different things you can measure with radar. But the simplest one, and the one where we've got a specification already, is normalized backscatter. So there are well-documented methods to normalize the backscatter for each polarization convention. And if you do that normalization, then you can pick up the radar data and use it as a time series and use it between instruments to monitor the land. So that left-hand side, there's product family specifications. They're the new thing that this framework brought in. There are additional product family specifications being developed for radar, and others will follow inevitably. But excitingly, we've got 3 actually nailed down in the CEOS community. And that took, 3 years. We've also got a process there, which is that once the USGS, once Tony's imaginings come to reality and they produce a data set that's analysis ready, they will then self-assess it against a series of criteria. And then their assessment will go to another group to check that they haven't, cut any corners. At which point there'll be actually an official, this is CEOS analysis ready data for land. So there'll be a specification and a point at which you do meet the specification. What that looks like is there is a bit of paper, and you can go to that website and chase it down. There are PDF documents of these things. For surface reflectance, it's a document that looks like that. It says, what are you trying to measure? Okay, it's surface reflectance. Some definitions, skip that. Then, okay, you've given me this bunch of data that you're saying is analysis-ready surface reflectance. Well, I want to know where it came from. So general metadata is the least you should know about a data set, where it came from. So this is, and there's a series of fields for this. And so let me explain the columns here. There's an idea of a threshold requirement and a target requirement. A threshold requirement is the least you need to do to meet this specification. Target requirement is where you'd really like to be. And then there's these other columns that allow someone to self-assess against those targets, to describe why they think they meet those targets, and then to suggest whether or not the target's reasonable. I provide feedback on the process. This whole bureaucracy is now something which is running within CEOS. Once you've accepted the whole data set, you'd start to use individual pixels. Well, there should be some pixel level metadata telling you whether that particular pixel is a no data value or is an invalid value. There's a section on what the minimum radiometric corrections should be in order to be analysis ready, and what the geometry should be in order to be analysis ready. So that's a long document, but what it's doing is simply formalizing all the things that are already people are starting to do, and to tie them down so that there's some minimum standard associated with analysis ready data that we're all starting to deliver. So this is starting to work, and here's a non-imaginary image of from Landsat 8, USGS Collection 2. Steve Labarge could probably talk to this, but this is what we're all looking forward to early next year in terms of global data sets, which is a surface reflectance that meets all of those criteria that CEOS have set out. ESA are similarly producing level 2 data and are going through a process of self-assessment against these criteria and reporting on how well they shape up. And JAXA, the Japanese Space Exploration Agency, has released global mosaics of normalized radar backscatter, which similarly are going through this process of ensuring that they meet all those requirements. Most of the non-meeting elements are around documentation and things like the request there be a DOI, and so they're relatively small issues holding people up in this. that's the normalized backscatter, but as I mentioned, there's a series, the radar community has really got behind this and started to talk about, for interferometry and other things, what are the products, the logical products that make sense from a scientific and operational point of view to be analysis ready. So they are now working on other standards, including polarimetric decomposition, about 3 or 4 other standards, in fact, which they'll probably have done this calendar year. So that will start to unlock all these data sets in a way that hasn't been possible before. CEOS is now saying, okay, rather than this being a small task on land and associated with one subgroup, we really want it to be a strategic initiative. CEOS, we think, is very important for the whole organisation, and so we're actually taking a strategic approach to this and driving it forward more broadly. And it's about the objectives of this, as up here, continued competitive performance of EO programs. This is really existential stuff for Earth observation programs. If these data sets can be produced according to a standard, are high quality, then they can remain the benchmark for analysis-ready data against which other systems can match themselves. Maintaining flexibility and adapting to an evolving expectations of the user base. The space agencies can see that their user base is moving to be operational and applied people rather than researchers. Take advantage of machine interoperability. So again, this is about positioning for future data architectures that the data need to be ready for use and machine readable to be leveraging those environments. And you can read the rest. And there's a few others. So there's a lot of several strategic objectives that CEOS is using to rationalise why this work is important. And so there'll be we'll take this strategy forward over the next year. It'll be endorsed later this year, and then the strategic implementation team, which Alex Held and I will co-chair, will have this strategy as one of 3 key strategies that CEOS will drive over the next 2 years. It will be the components of these technical specifications, was what I just spoke about, continuing that, starting to produce the data, trial the data, get feedback on the data, and continually refining those standards. So each year they'll get revisited in terms of whether the standard itself, the specification, is fit for purpose, or whether there's things in it that are ambiguous or unnecessary or not sufficiently stringent or too stringent. There'll be a very visible stock take and outlook of here are the products that space agencies are producing that are meeting these analysis-ready data specifications and what's coming next. We'll probably see the evolution, as I said already, of new product family specifications, and then there's some exciting concepts like what do you do with new sensors like ICESat, for example? How do you make that analysis ready so that you can really leverage the data? Pilots and feedback in terms of pilots and feedback will take us into the next space, which is, okay, the analysis-ready data may exist, but are they fully discoverable and accessible and utilizable? Are the file formats optimized? Can you get them through, find them through a STAC mechanism? How quickly can you link them into an open data cube or some other analytical framework? And the last one is probably one of the most important, which is about promotion. So at this point, CEOS is in a, and me standing here is CEOS getting into a space that hasn't traditionally been comfortable with, which is we need to interact with the broader community on this and get feedback from the private sector. We can see here a framework that others could use and a framework where we can bring other data together. So there's a lot of opportunity, I think, to work here together across communities in this promotion space. So as I mentioned, there's an upcoming meeting in September in Anchorage where this will be taken further forward, and those of you who are involved with CEOS are very welcome to get involved with that. And then there's another big opportunity happening in November at the Geo Plenary in Canberra. there'll be side events, and there's a side event going to be at that called Big EO Data. There's a very limited number of side events at the Geo Plenary. It's a 1 week ministerial international get together, which will have very high profile. We're pushing there to have, we've successfully got a side event on analysis ready data, which has been tagged Big EO, Big Data. That's a real opportunity. There'll be a strong industry stream at this Geo meeting, so it won't be just government. And that's an opportunity to talk about where data are coming from, how they're going to be made analysis ready, where they're going to be housed and landed so that they can have maximum impact globally going forward. So please think about going to Canberra in November. There's some good things there. Also, as part of that strategy in CEOS, there'll be a workshop some stage in 2020, don't know when, where we will, I think, be actively targeting industry engagement. Whether that's in the US or Europe or somewhere else is open question, but that's where we'll be going next. So I think this is the first, probably the second time this meeting's heard about CEOS analysis ready data, but we want to actually take that up a level in the coming year. There's the contact points there. Matthew at symbioscomms.com is really reliable. Steve Laban's really reliable too, or you can email me. Thank you all. Cheers.
Great talk, Adam. We have some time for questions for Adam, if anybody would like to ask.
Steve, is there anything you want to add? Oh, sorry.
I just wanted to ask for you or for others in the community here, is this integrated with the STAC's metadata at this point, or is there a plan for doing so? Can I discover whether data is CEOS compliant through STAC's catalogs?
So one of the things, when we started this, we made a really conscious effort. Just focus on the thing called analysis ready data. Don't talk about whether the data is open license, for example. Don't talk about its cost or the file formats or any of that. So that was a conscious effort to focus on the bit of the problem we knew we wanted to address. The next stage, having got to this, the focus is now moving on to exactly those things. Are the file formats going to be effective? What's our advice in terms of packaging these things? And are they discoverable? And I think that will take us very rapidly and in a pointy way towards other data in STAC compliant formats and working through those frameworks. So yeah, I think that's next. And there's a group in CEOS called the Working Group for Information Systems and Services that I hope will pick that up pretty actively.
Okay.
You're not allowed to ask questions.
I get one. Hey, I just want to make a real big extra mention of this engagement we'd like to have with the commercial and the broader community here. And so I know Adam talked about both this LSIBC meeting come up in Anchorage in the Geo Week, and then this ARD workshop next year. But I guess we really encourage involvement by all of you and any of the data providers out there, because if we can get our communities working together in a common way, in a common standard, I think the end user is the benefactor of all of that. So just really encourage that participation, and you can follow up with any of us after this meeting. Any questions about that?
Yeah, I really underdid that. You guys are a really powerful and important voice. One of the things that the space agencies look to and question in this framework is what users are asking for this. Who cares about it? The fact that these meetings are happening says that the broader community care about analysis-ready data, but the broader community need to feed back to the space agencies about the adequacy and the direction of this program in order to influence it for good. Forgot what else I was going to say. There was something there. Whatever.
Something very wise, I'm sure.
Other question? I forgot to thank Steve for doing pretty much 90% of the work on the presentation.